When a region is revolved about a line which is not one of its boundaries, its volume is formed from a sum of volumes of washers. At least some of the disks have holes in them. The washer formula is very similar to the disk formula where we have pi times the integral from a to b, but inside our integrand is the outer radius squared minus the inner radius squared. For example 3b, we're going to revolve about y equals -1. This means that our axis of revolution is not the same as one of our boundaries. This distance right here is called the inner radius. So little r, our inner radius, is 1. The distance between this purple curve and the x-axis is -x squared plus x. So then our outer radius, that height is just giving us the distance between the curve and the inner radius. But the full length of the outer radius, big R, is -x squared plus x plus that inner radius, 1. Now we can set up our integral from 0 to 1 to find the volume of this solid. This is the integral setup for the volume formed by washers here. When revolving about y equals 2, your axis of revolution is above the x-axis, and usually the heights are given between the curve and the x-axis. So we're going to have to really try to visualize what's happening here. Our outer radius is unchanging. It is always going to be 2. Now how far this inner radius goes in is dependent on the height under the curve. Remember that this distance right here, or any of these distances, can be found by -x squared plus x. That means that little r is our full radius, big R, which is 2, minus the area under the curve. This makes our volume, again from 0 to 1, big R squared minus little r squared. And there's our integral setup. For example 4, set up integrals for the volumes of the solids formed by revolving the region bounded by x squared and x plus 2. They've already drawn a representative rectangle here. It looks like big R is given as the distance from the line to the x-axis, which is x plus 2. It looks like little r is the distance between the quadratic and the x-axis, which is given by x squared. So our volume is equal to the integral from a to b of big R squared minus little r squared. From a to b, it looks like it's -1 to 2, just in case we make these equations equal to one another to find our intersections. -1 to 2, we're correct. This time we're revolving about the line y equals 4. Remember, when this axis of revolution is above the x-axis, it definitely makes for some strange subtraction that we have to account for. First, to try to visualize the object, our outer radius is the distance from the axis of revolution to the quadratic curve. This is our outer radius. And our inner radius is the distance from the axis of revolution to the line. It's very tempting for students to think that big R would just be the quadratic and little r would just be the line. But remember that this is the height from the x-axis. But if our revolution is way above, we have to make a subtraction. We do know that big R can never be larger than 4. The distance between the line and the x-axis, we do know, is x plus 2. This makes our inner radius equal to the distance from the axis of the revolution to the x-axis minus the distance between the line and the x-axis. This height is x squared. To get big R, I need to take the distance from the axis of revolution to the x-axis and then subtract the distance between the x-axis and the quadratic curve, making our volume, again, from -1 to 2, big R squared minus little r squared. And there are the integral setups for volumes formed by washers.